Konrad Werner, who is right here with us from the University of Warsaw and visiting HPS this semester, is going to be giving us a lecture. Today, it's my real pleasure to introduce Aydin Mohseni, who is a postdoctoral fellow with us this semester. We've been really happy and lucky to have him with us for the whole semester, for the whole year, actually. He got his PhD from LTS Irvine, and his advisors were Simon Hüttiger and our good friend Kellen O'Connor. The title of the dissertation was Essays on the Social Epistemology of Science. Coming back to Pittsburgh was in some ways coming home. I mean, in some ways, because he got his MA, or actually MS, I guess, from CMU on logic, computation, and methodology. So Aydin worked on a range of topics in philosophy, including various methodologies, issues related to social epistemology of science, to games theory, to the replication crisis, which we'll hear about today. He's done some experimental work, some formal work. So it's really a rich research program, and it's published in all the best journals: Philosophy of Science, PGPS, Philosophy of Science, FFPs, and CTES, and so on and so forth. We are really lucky to have him at the podium. The floor is yours.
Thank you all for having me. Today, I'll be talking with you about HARKing, a putative questionable research practice. It's misdiagnosis and misprescription. And if I'm successful, I will have left you thinking very differently about HARKing than perhaps you have right now, and hold on some deeper and broader threads as to how we might go about changing and improving scientific methodology quite generally. A backdrop to this project might be something we talk a good deal about: the replication crisis in the social and biomedical sciences. Against the sobering findings of alarming rates of failed replication, of the inflated effect sizes, of the anti-correlation of journal prestige and replicability, the community of meta-scientists, philosophers of science, all the stakeholders involved have been thinking about how might we change the norms of science to move toward a better state, to navigate the space of possible scientific inquiry to something more ideal. And in the space of suggestions, right, we have things like redefining the conventional threshold for statistical significance, promoting pre-registration broadly and understanding what that might consist in, and revisiting and either augmenting or wholesale replacing classical statistical methods for analysis. And this presents us with an opportunity, I take it, to look at deep questions that, in a sense, we were always interested in and should always be on our radar. What are better and worse norms for science? And what are the consequences of changing those norms in scientific practice? And perhaps quite generally, how do we navigate possible science into our future? To competently assess these sorts of norm changes, some of the broader pieces of my work are that we need certainly the right statistical theory for scientific inference. And for my money, this is going to be Bayesian inference. And an adequate social epistemology of science, right? One that accounts for facts like scientists influence one another and respond to incentives. In this talk, I'm going to look at how current accounts of questionable research practices imputed in the replication crisis, in particular of HARKing, or hypothesizing after results are known, are wrong. I'm going to provide a Bayesian account of how HARKing actually interacts with the reliability of scientific findings. and examine the implications of these mistaken understandings of HARKing for at least one prominent proposal for addressing some of the ills of the replication crisis, that of thinking about how one might redefine statistical significance. Good. So HARKing was first introduced to the literature and coined by the psychologist Norbert Kerr in his seminal 98 piece on the topic, where he defines it as the presentation of a hypothesis selected ex post to observing the data, as if it were one selected to ex ante to observing that data. This should be contrasted with the ideal picture of science, where first the researcher selects her hypothesis and then observes the data, which is used to test it. Notice that there's an inversion going on here, where in HARKing, the data is observed and then the hypothesis selected. So the main accounts in the literature, if we look at it as to what is wrong with HARKing and why. First, let's animate that indeed people are very worried about HARKing. This is the psychologist Dorothy Bishop in a Nature opinion piece articulating or describing HARKing as one of the four horsemen of the replicability crisis, along with publication bias, low statistical power, and p-hacking. For our first account, of why this is so, why we ought to list it there, next to underpowered studies and p-hacking, is that HARKing undermines the frequentist guarantees of the reliability of tests. And this is a very natural and long-standing objection to HARKing. The other comes out of perhaps the most prominent account in philosophy of statistics, or a kind of sophistication of the classical account. This is Deborah Mayo's severe testing account, which identifies the problem with HARKing as having to do with it violating the requirement of providing a severe test of a hypothesis. And finally, there's kind of a broad cluster of objections that malign HARKing for misrepresenting when the hypothesis. My claims are going to be that none of these is right, that the right account is a Bayesian one, and that misdiagnosis of HARKing has implications that we should care about when we're thinking about how best to tailor solutions to the ills that we've identified in the replication crisis. Now, to clear the ground, I also want to be quite transparent about what I'm not saying. I'm not saying that I'm in favor of HARKing when it involves intentional deception or disclosing less than complete information. We have good reasons not to prefer that. We can look straight to Bayesian value of information theorems to think why we should always expect with less information, to do more poorly relative to our aims. Insofar as HARKing involves failing to communicate an accurate model of science to students and so on, none of these are good properties. And I would defend none of these aspects, potential aspects of HARKing. Rather, I'm interested in the following question. How precisely does HARKing interact with the reliability of scientific findings? And our first step is to see why some of the standard accounts identify that fact, the nature of that interaction. And the structure of my argument is going to be that each account claims that HARKing undermines the reliability of scientific findings because it exhibits a particular property. Then I should show that HARKing can increase the reliability of findings while still satisfying that property. And that property cannot explain why HARKing undermines the reliability of scientific findings. Just to elaborate on those three accounts, of a clear picture of their logic structure. The first one observes that it follows very naturally from a frequentist conception of statistics, where the frequentist locates the reliability or reliability in general in terms of the error control and hypothetical infinite repetitions of her tests. She gives you certain sorts of guarantees. For example, if we choose a significance threshold of 0.05, we can see how HARKing undermines this sort of a guarantee. This idea is if one were to repeat this task with this significance threshold indefinitely, under the assumption that the null is true, 5% of the time one would mistakenly reject the null. Right? The limiting frequency of false positives would be 5%. So assume, right, again, that we're in the world in which all hypotheses are false, but we're doing a HARKing protocol in which we test 20 hypotheses, and afterwards we select one to report that happens to be significant. Notice that the probability of reporting a false positive is no longer 5%, but 64%. And so we kind of nicely described, again by Bishop, that as p-values being meaningless when taken out of the context of the analysis performed to get them. Under the severe testing account, it should be perhaps kind of immediately intuitive why HARKing would run afoul of its requirements. Where here, what we want is a statistical test for a statistical test to provide us with warrant for corroboration of a hypothesis. It must submit it to a severe test. Where a severe test is one that modally would detect an error in the study hypothesis if one were present. One could think of this as a kind of data-dependent analog, as in the p-value, for power. And insofar as HARKing involves omission of non-significant results for a given hypothesis, we look at the data and then choose something by construction that is significant. It fails to provide any non-significant results, and therefore a severe test of any hypothesis. I could have never told you this hypothesis turned out to be non-significant. So modally, right, if there were any issues, I would not have reported them to you. And the last kind of cluster of misrepresentation objections, right, that we are misrepresenting when a hypothesis was formulated, are kind of hard to pin down. At times they have a more ethical bent, at times they have an epistemic bent. They think that this affects reliability. There's no typically account of how reliability is affected. But we'll see that something actually like this last account might well be most close to the truth. That is a misrepresentation when it occurs that is in some sense most problematic. Good. So for us to run an argument that a particular method, HARKing, undermines or improves the reliability of scientific findings, we should define our notion of reliability. Classically, we want to have our studying methods produce fewer false beliefs and more true ones. In the context of null hypothesis significance testing, we can ask that fewer the results or hypotheses we declare significant be false, and fewer the results we declare non-significant be true. Straightforward translation of what we would want. And these correspond to the requirement that our methods exhibit lower false discovery and false omission rates respectively. And these are actually quantities that that were introduced into literature by frequently statisticians, Cohen and friends, 30 years ago. And their logic is pretty straightforward. A false positive occurs when a study yields a significant outcome when the null is actually true. The false discovery rate then is equal to the expected number of false positive outcomes over all significant outcomes. This is the value for which the failed replication rate is an estimator. When we worry about this in the context of the replication crisis, we say, look, of our studies in this field, 66% of them fail to replicate. That is an estimator for this underlying quantity. A false negative occurs when a study yields a non-significant outcome when the null hypothesis is false. And the false omission rate, correspondingly, is the expected number of false negative outcomes over all non-significant outcomes. You can think of this as a fraction of things that we said were non-significant that were actually true. And now we can lay out an operationalization of reliability. Consider some population of studies fixed by the false positive rate and negative rate of its tests, right? So the significance and power of those tests in that population of studies. along with the fraction of true hypotheses from which candidate hypotheses are selected. We say that a given protocol for reporting findings is more reliable than another if, for any such population of studies, findings produced employing the first produce a lower false discovery and false omission rate than those produced using the latter. So regardless of those statistical properties and those kind of maximum values on the unit interval, if one exhibits a lower false discovery and lower false omission than the other, you can comfortably say it's more reliable as a protocol. Good. Now, the proposal here is that this is going to capture our working notion of reliability. More of the things we say are true, more of the things we say are not. Right. And a method is more reliable if, regardless of the kind of tests and the background conditions, under any of them, it does better than the other. Now, we might have more nuanced pictures. We might say, look, what if a method's better under some conditions? That's fine. But certainly this should be something minimal that we admit. If one is better, no matter what, that method is better or more reliable. And that method that I'm thinking of, we're going to be talking about prediction and HARKing. Those are the protocols that I'm sketching. Good. So why not the classical frequentist error rates? Right. To see why those kinds of measures of reliability are not the right notion of reliability that we want to work with, you can consider a domain of science which no true hypotheses are available, because this is a null field where the null hypothesis is always true. Regardless of the type 1 and type 2 error rates of tests, all significant findings will be false discoveries. Right? It doesn't matter how well powered my tests are or how low my significance threshold are, is everything that I find in this field will be a false thing. Good. Notice, however, right, this just points out a straightforward fact. The same frequentist guarantee I gave you for type 1 and type 2 error rates is compatible with any reliability of a scientific finding, since the reliability is critically a function of the prevalence of the hypothesis put to test. And to kind of get a very kind of concrete, intuitive picture, imagine changing the background theory, which affects the kind of hypothesis you tend to test. Are you in particle physics? Or are you in nutrition science? You could have the same power, right, and significant threshold for those two. We'd expect wildly different reliabilities of hypotheses that get reported as significant. And those error rates, contra false discovery, right, and false omission rates are not going to be sensitive to the differences between those fields. Or methods, for that matter. Yeah. And then to see how that applies straightforwardly, the method, pick a method that starts with just choosing all false hypotheses, and pick a method that starts by choosing true hypotheses. The same shortcoming applies to any such measure. If we consider, well, what about p-values? What about test severity, right? Kind of data-dependent analogs. Well, insofar as the measure ignores the prevalence of true hypotheses submitted to testing, it will assign the same measure of reliability to a set of findings assured to be false as to a set of findings assured to be true. So let's consider when HARKing cannot be bad, right? To go through a demonstration of why the classical explanations aren't capturing the right thing, right? To explain the interaction of HARKing with reliability. So let researchers select their hypotheses from a set at random, right? This is what our researchers are doing. They reach in to an urn of hypotheses, they pull one out for testing. This is equivalent to saying the prior odds of all the hypotheses being equal. So your predictive odds on any hypothesis for being true should be just 1 over the number of hypotheses. Suppose a researcher observes some data and obtains the p-values for L independent and extant identical hypothesis tests. Consider the reporting protocols the following. First, let's begin with prediction and specify in kind of natural description of prediction. Test a single hypothesis. So select the hypothesis, ex ante, observing the data, observe the data, and then report the hypothesis if it is significant. HARKing. Right. Now we shift when we select the hypothesis. We don't commit to any hypothesis before observing the data. We observe the data, and then we report a hypothesis chosen at random from among those that are significant. such a one exists. And we can consider a slight sophistication on HARKing, which is report the hypothesis with the lowest p-value after observing the data. Again, we don't commit. We observe the hypotheses. We find the ones that are significant, but now we will report not just a random significant hypothesis, but the one with the lowest p-value. The first result that follows from this setup is that when the base rates of true hypotheses selected via prediction and HARKing are equal, we have these scientists choosing at random, prediction yields the same false discovery rate as HARKing, both exceeding the false discovery rate of selected HARKing. And the false discovery rate of selected HARKing is decreasing in the number of hypotheses. So prediction and HARKing must be identical in the false discovery rate they produce as protocols in this case. And they're both outperformed by slight sophistication of HARKing. And one can think through why this must be so, through kind of thinking through the logic of the filtration happening. Under prediction, right, the researcher has her hypotheses that a fraction pi of which are true and 1 minus pi of which are false, from which she's choosing, right? She commits to one, she chooses one at random. And if we were to repeat this process a bunch, right, the frequency pi of the hypothesis she chose would be true, and 1 minus pi would be false, right, for predicted hypotheses. And this is submitted to normal significance testing, right? So we get that of those that were true, right, the power will make that fraction significant, and of those that were false, the false positive rate will make that fraction significant. And this will be our significant results, the fraction of which are true, the fraction of which are false. So we filtered in that way. Under HARKing, we have the same set of hypotheses we start with. A researcher, she does not filter them. So now they're all present. And again, just as in the case, they have the same fraction true and false hypotheses. But now she chooses one. And she chooses one that's significant by construction. Right? So that's the same as choosing the ones that are significant because they were true. Right? The true ones times the power, and the false ones, right, times the type 1 rate. And it yields precisely the same ratios. The difference being that this is a much more efficient protocol. Because this tests a lot more hypotheses at the same time. And if we're wondering about false emission rates, again, they have to be identical for similar reasons. So with respect to false emission as well, HARKing cannot be outperformed by prediction. Indeed, they must be identical and outperformed by selective HARKing. So notice that HARKing satisfies each of these conditions. It absolutely undermines frequency guarantees, right? They are suitably meaningless in this context. It violates the requirement of providing severe tests. I was not giving you modally, right, non-significant results and telling you about their non-significance under this protocol. And it misrepresents when hypotheses were formulated while being at least as reliable as prediction. So, right, none of these particular properties are explaining what's going on and why HARKing is undermining the reliability of scientific findings. So when must it be bad? And the conditions we just described, and the critical one that I highlighted for you, right, was that equal prior odds of hypothesis selected via prediction and HARKing. The thing that I kind of motivated with the mechanistic procedure of the random science, right, or the scientists who draw a hypothesis at random. Hypotheses exposed to observing the data cannot undermine, this HARKing cannot undermine the reliability of some findings. So some assumption about that, if HARKing is bad, some assumption that I just made has to be wrong, right? For us to be in a situation where HARKing is bad. The natural one that we can relax is that scientists don't in fact choose their hypotheses at random. The hypothesis a researcher chooses prior to observing the data may be informed by theory, right? By previous literature, by common sense. And when a researcher is suitably informed, the hypothesis selected is more likely to be true than a hypothesis selected at random. Think of that as what it means for her to be informed. Good. In such a case, we can expect the researcher to do better than chance, right, prior to observing the data. If you told her before she got her results, I want you to make a prediction, she would do better than total chance at a prediction of which of the hypotheses would be true. In contrast, when a researcher is engaged in HARKing, she's no longer filtering the set of hypotheses, right, via her domain knowledge. Rather, what she's doing is saying, of the ones that were significant by noise, by error, by being true, right? I'm going to pick one of those to submit to report it. So with prediction, she's filtering the hypotheses with an additional level of filter. She's changing the prior odds in a way that with HARKing and with the way we described, she's not. And formally, this corresponds to a model in which the researcher chooses from two sets of hypotheses with different fractions of true and false hypotheses. When she chooses that she's observing her data, right, via prediction, she tests the subset of hypotheses with some of prior odds. When she chooses ex post observing her data by HARKing, she chooses from a superset of those hypotheses with different prior odds. And if she's informed, those will be lower prior odds. So this proposition gives us more generally the conditions under which HARKing is going to be good and bad. So let a hypothesis selected via prediction and HARKing exhibit their own base rate. Then prediction is more reliable than HARKing with respect to false discovery, just in case the base rate of hypotheses selected for prediction is greater than chance. And we can come back to our filtration diagram and recognize that the choice point of prediction has to change these base rates. And it has to improve them relative to the baseline by chance. And then prediction can produce better odds. And now I've suggested that the most natural thing there is researcher judgment. That is making that change. But the researcher knows something that makes her better than chance. It also provides us now with an explanation of this kind of misrepresentation objection. Why is that actually kind of glomming onto something? Which is that if I expect a researcher to have reasonable domain knowledge, to know her area of expertise, right, then I expect actually her choice of a hypothesis, that was the one she committed to and chose to test in this study, to be itself evidentially relevant. I expect it to make it more likely for that hypothesis to be true. And what she did was she just picked one that was significant afterwards, that worked out with her data, and then she represents it perhaps by storytelling or just not telling me, right? This becomes problematic because intuitively, right, I'll assign a greater credence to her finding, and this can also support the way we feel about additional storytelling. You can think of in particular areas where we're creative storytelling and we make it seem obvious, or we're making it seem it's like the hypothesis had a much higher prior odds of being right, even before the test was run. So HARK or not the HARK? When one or the other? This kind of analysis also gives us an idea of when HARKing will produce more reliable findings than prediction. Consider an unlucky world in which a scientist's judgment is anti-correlated with the truth. Right? That is, when the researcher makes a prediction, she selects false hypotheses at a rate worse than chance. In this world, it's straightforwardly better than HARK. However, if the researcher's judgment is not much better than chance, it's important to notice that prediction is when prediction is much more limited, when judgment is much weaker, right? Then it might be preferable to HARK because we know that they also have efficiency properties, right? We can test a bunch of things at once, just notice the things that are compatible with data. In an exploratory analysis, that might be exactly our priority, right? And when should we expect ourselves to have kind of be poorly informed about the domain? Right, our prior odds as researchers to be not great is when sometimes the hypotheses are massive in terms of set. You can think of certain machine learning contexts. What is the right neural network to identify cats? That's not the kind of thing I'm going to have reasonable credences over. If it's highly complicated, or when researchers are known to be biased. You can think certain political domains, I might know that I'm biased in this case. I might even do worse than chance here. And the question about, so when should we think of researcher's judgment as better and worse? There's actually good studies looking at things like prediction markets of a hero of psychologists for replication studies of other researchers' work. We show we're often not bad. It's actually remarkably good performance for psychologists identifying when their colleagues' work would replicate or not. So the very notion of how good is researcher's judgment is not something out of the purview of what we can predict. right, or estimate. Good. So my third claim was that the misunderstanding, that's the basic character of what is the logic of the interaction of HARKing, right, with reliability has consequences, and it can lead that we should care about when we're thinking about how to change norms, like against the backdrop of the replication crisis, like what are better methods, right? In particular, we can think about proposals like this one, right, in which in human nature, we have several hundred prominent methodologists thinking about, hey, if we lower the significance threshold from 0.05 to 0.005, we think the simple step will immediately improve the reproducibility of scientific research in many fields. And this is really not a at face value unreasonable proposal. I think that in fact, this has got to be right in certain cases. With the caveats that we entered of, some of us might want to move to Bayesian methods and think that there are better ways fundamentally to approach statistical analysis. But realistically, we're going to be using things like non-hypothesis significance testing for some time in the future. So it behooves us to think about how to do it well for as long as we are. And certainly the current value of significance for any given field is unlikely to be exactly the right one, right? Are we exactly calibrated? So this proposal, in some important ways, should be right for some cases. The question is then what value and what consequences? And I very much like this article and it's worth reading. For any of you who have it. Notice also to kind of promote the idea that we can do this. Fields like genomics and high energy physics have profitably set more stringent standards for their conventional thresholds, right? In the context of things like GWAS and particle detection and so on. So you know that there are some cases where perhaps it works quite well. But there are differences between domains of inquiry, and we have here Unides worrying out loud regarding the efficacy of lowering the significance threshold in the social and biomedical sciences in particular, citing the relatively greater researcher degrees of freedom in those disciplines. He says, adopting lower p-value thresholds may produce collateral harms. Bias may escalate rather than decrease if researchers try to find ways to make the results have lower p-values. And I can think of the model I'm about to produce as one way of thinking of vindicating the possibility of this intuition being onto something. Right. So to see why this kind of intervention makes sense, and also to see how it might interact with HARKing in the logic that we just described, consider the following simple model. Researchers are engaged in a strategic mixture of both prediction and HARKing protocols. A researcher follows the protocol of prediction when she can and HARKing when she must, in order to get statistical significance for some finding, and so to publish her study. Bouncing around a bit here. So this protocol I'm going to call fallback HARKing. What the researcher does is that she does the salutary thing, chooses her hypothesis before observing her data, and if she observes her data and it's significant, she reports that hypothesis. But if it's not significant, she still needs to publish. So she needs to find something significant. So she turns to dredging her data. And among the hypotheses that happen to be significant, she'll find one of those and report that. And under representative background assumptions, and we can talk about those, one sees that this can actually increase the false discovery rate of literature produced in this way, under this protocol. Here in our graph, we have the significance threshold right along the x-axis, the false discovery rate of the literature across the y-axis. We have prediction here. Notice that if everyone was engaging in predictions, the lowering of the significance threshold would just straightforwardly lower false discovery in the way that we expected, in the way that we want. What was happening here that is producing the kind of explosion of false discovery is that while reducing alpha, the significance threshold, reduces the false discovery rates for both primary and auxiliary hypotheses, it also increases the likelihood that the researcher will be pushed off of her primary hypothesis, the one that enjoyed, importantly, her good background knowledge. Here I'm assuming that her priors make a hypothesis twice as likely as chance to be true. Right? So she'll be pushed off of her hypothesis onto whatever happened to be significant. Right? And those auxiliary hypotheses will, in expectation, enjoy lower prior odds. And this can increase the false discovery rate for now that published literature that we get as a product of this kind of a dynamic. Note that in this sort of a case that we just looked at, correctly identifying the mechanism by which HARKing affects the reliability of studies, the differences in expected prior odds of hypotheses characteristically selected, ex ante and ex post observing the data. The logic that we analyzed together was crucial for identifying the very possibility of the undesirable consequences here of extreme values of that intervention, or even its logical structure. Right? That under this kind of a description of what researchers are doing, you notice that it's going to get worse, but then it can get better. Right? The very dynamics would be not visible until we had articulated how is HARKing interacting with reliability. Yeah, and that effect could not be characterized just by looking at type 1 or 2 error rate, p-values, or test severity. Our moral then is that when researcher judgment on a problem is well informed, lowering the significance threshold can push researchers off of more promising hypotheses and onto dredging many unpromising ones, and so can in fact increase the false discovery rate of findings. When this is so, I believe there's a slide in which I articulate the underlying conditions that we want to be sensitive to, but we can come back to that. Conversely, when researcher judgment is limited, when we're facing tasks where the set of relative hypotheses is very large, highly complicated, or researchers are known to be biased, HARKing can outperform predictions. And the current accounts of HARKing that stem from a frequentist philosophy of statistics fail to explain the actual logic of its interaction with the reliability of scientific findings, and that their misdiagnosis can lead to misprescription for solutions in the context of the replication crisis. And the Bayesian analysis of this problem makes this all clear. Thank you.
We take a 2-minute break. I already seen your hands, Sandy, so you're already in. We take a 2-minute break in case you need to leave, and then we'll have half an hour for Q&A.
Oh, yeah. I filled up a big glass of water to bring over and go, oh, I had to drink this before. I drank all this water before. We're coming in this direction. Morning, when I went to this
Yeah, keep track of
the
the
wrong building. So then I was in my car because I didn't know.
yeah,
So I hooked myself over to the right building, got it.
Oh, I listened to the HARKing captions. It was so good.
Oh, I'm glad.
The guy, like, it was really good analysis. And
Good.
it's just so nice to hear someone who
Right.
understands exactly
I love it.
how hard.
I don't think I agree, but let's see without my question. I do agree with you.
Or failing last time.
You get your points from
The
it.
second thing was carbon capture.
I do worry a little bit about the
It's
way
like 15% of the solution.
Oh, that's great.
It's not like,
Or you
like,
know,
with
are
everything, that actually is like, you have all the wedges.
It seems like it goes.
It's just like large enough. Everything else is like, you know, a little thing, a little thing, a little thing, a little thing, a little thing. Right, like, you know, that's the kind of
Yeah, actually, I went to I highly recommend it.
Which is why I'm like, don't generate.
So you're looking into the solar option.
And other facts.
But I don't know how far we should do that to our plan.
Yeah,
Like
It's a 1 hour, it's a 1 hour
House
visit.
on batteries,
That's
I
what
could
you
run
do.
the solar on there before
In
the-
hallway, because there's some.
Yeah, I mean,
so we'll see.
Just.
For you all, like,
Yeah.
I'm sure. And then you can do solar like when you want to charge more, but you don't have to charge without.
A little bit short, because at the end, there's some gas.
Yeah, it was.
As long as-
You're trying to juggle everything.
How long it lasts.
You're not certain about that part of the exhibition, but that's a little bit.
How long?
That's about it, what I need.
The
Interesting.
worst was about 4 days.
Yeah.
That was launched in 20 years.
I went to.
Actually, my partner,
This is really criticism.
I don't say much about in terms of advice. Last week there was a Zumba workshop.
Differential.
Friday.
Battery.
Well, I don't know. But in any case, you know, the times.
And on Saturday. It's by your school, one of the one I really those stuff also. It's a have parties on.
No, this is here. Yeah, I'm literally sitting.
As I do it. I mean, I don't know.
Yeah, so after you like, you know, have this terrible.
It is a Sandy, you don't have time to think. It's time now. Guys. Before we start, excuse me. In the audience, if you have on Zoom, if you have a question for us, please put your name in the Q&A box. Click on Q&A, put your name, and if we have time, we'll add you to the list.
I think
Yes, there's already someone. Yeah, I'll. What's that? No, I think there's mic in the room, so I think don't hear that. Thanks. In principle, they should have a. Sandy, go for it.
Thank you. That was really fascinating talk. I really enjoyed it. I have a question though, because my tendency is to think about implementation issues here. And so you give us, so there's some, the advice you give us at the end is that when and when not to HARK depends on whether or not the scientist is more or less likely to have good prior hypotheses, right? But how do we know when that is, since we have no access to what you refer to a few times as the actually true, which seems to be a little bit of a concern in implementation? Then how do we know whether they are more or less likely to be true in order to apply this as an actual prescription to working scientists?
Yeah, great question. In thinking through that part of implementation, here are the following levers that we have available to us that I would argue are better to be pulled than not. First, I mentioned that we need more than an estimate of the researcher's judgment, right? The amount that improves hypotheses over kind of their base rate. We also, of course, want to know the prevalence of behaviors like fallback HARKing, which is its own challenge, right? And questionable research practices in general, which is its own challenge. Power, average power in that field, where the significance threshold happens to be for a field at the moment that we're doing the intervention. And for each of these, there is in fact work reports looking at that. Some of them are straightforward. We know where we've set the significance threshold. We have lots of surveys of mean power in fields. The prevalence and impact of questionable research practices is something that we have some estimates by when you observe things like now we pre-register, now we don't. These are kind of not perfect estimates, but they begin to give you a sense of magnitude. That notion of how much does researcher judgment increase the likelihood of something being true is something that, again, can be estimated. The Kammer et al. Article that I gave you that began to look at how well, in fact, scientists do when you ask them to predict things, accompanied with what are called the replication markets, where you have folks, again, betting, both scientists and non-scientists, to get how good is their judgment with and without data, before and after tests. So that
We're getting an assessment of people's assessment of.
That's right. So when scientists make judgments, how much does that actually impact the likelihood of a hypothesis being true versus when they just give the assay of, I'm throwing everything in the kitchen sink, I'm not betting it, I'm just throwing every one of these agents to see whether one of them has, in a cancer moonshot, makes an impact, versus no, I want you to pick out the agent you think is most likely to have the effect that you want, right? So in those cases, you can get at precisely the quantity that we want, and there are studies doing that. It's hard. You're absolutely right. I think it's important to attend to how it's difficult. My observation or my proposal would be that it's very worth doing. And I think that what you point at is a really important and critical part of this sort of sophistication that we want to be adopting in the coming years.
Then come back if you want. And go for it.
Hi, yeah, thanks. Interesting talk. I was wondering if you dealt with well, probably didn't deal with every way that you might think HARKing was problematic. And I think there might be some ideas about severity that are rather older than Mayo, kind of go back to Popper and the critical rationalist tradition, some ideas of severity of testing there. And particularly the significance of novel predictions and unexpected predictions. And my basic wonder, my basic thought is that HARKing might stop you or discourage you, the ability to hark, might discourage you performing particular kinds of experiments. So it might change the kind of experiments that actually go on in science, right? And this might have an effect. So the idea would be something like this. For a good Popperian scientist, roughly, you would take a hypothesis and then you would look for, I think a severe test would be predicting some evidence that the probability of the evidence was really, really low. And you choose the experiment you perform on that basis. Whereas if you're HARKing, it doesn't seem you're going to follow down the same routes, right?
Yeah.
You're not going to search for novel predictions in the same way and test that hypothesis may be so severely of that kind of corroboration style measure. Does that make sense to you? Does that seem like something you could add into your account? That also it's going the price of the evidence won't affect what happens in the same way as well. Something like that.
I think that sounds very true and also very interesting. Right? One could look at further issues that HARKing produces. And you're absolutely right that in this account, I definitely don't attempt an exhaustive survey of all the different sorts of things that could be wrong with HARKing, even purely epistemically. But this focus was very much on, okay, its reliability, its effect on reliability.
Sure.
Right. In the very straightforward null hypothesis significance testing framework where you have many of the features in the background fixed. But I love your suggestion that of thinking through, right, researcher choice of tests comes with expected informativeness in that classical style of, right, how much are we going to learn? And if I'm understanding correctly, we can now think, hey, if I can just submit a bunch of hypotheses, which is what HARKing often allows me to do, and feel comfortable about finding something that's significant, right? I might not be as incentivized to find those extraordinarily discerning hypotheses in order to kind of meet the threshold of accepted value to get something out of that study to be able to publish. I think that's really interesting. That's definitely something that one could think about in general. Another level of how HARKing could interact with incentives, and how the one thought is, yeah, yes, that's right, that's interesting. And I think it's worth thinking about in the broader kind of projects that, like the open science framework type projects that try to think, okay, how do we do pre-registration with the right incentives, right?
I mean, A related issue, just to mention one other idea, might be that I think you're perhaps focusing on a slightly synchronic notion of reliability, whereas if you thought about it in a more diachronic fashion, about what happens in the kind of experiments that are performed over time, then what I just mentioned might be relevant to that as well. So.
That's right. That's right. There's almost surely, if we were thinking about how to navigate science well, if not science is at a moment, I want the next moment to have this notion of reliability. I might want to do things like, as you put it, even in the background, how important is the test, right? There's some things I could find out that are true that we're uninterested in. And there's also sequential effects, as you mentioned, right? That you could think these results could open up some kind of sophisticated notion of, right, diachronic dependency of what results in power for future study. I think that sounds all right and all interesting and valuable stuff to study and consider. I love the suggestions.
Ask the question.
Thank you. That talk really fascinating. I'm really happy about the way that philosophers of science are now really engaging with real world scientific methodology and statistical analysis, the way it goes on out there in reality. But I'm also wondering now about some old problems. I mean, there's a clear affinity, or at least an apparent vague affinity between the HARKing issues that you're dealing with here and this old problem, the problem of old evidence. And if I recall, Hausen and Urbach gave us a Bayesian analysis of that problem, right? And what I'm wondering is, does your analysis here paste back onto the old problem of old evidence? How do you see the relationship between them?
Yeah. Good question. At least initially, it's not clear to me the relationship. Maybe I could invite you to say more. The thought was, I typically take the problem of old evidence to be one for the ideal Bayesian agent. Right? That is to say, the agent who is closed under deduction, right? Grappling with how to learn logical relations, right? Yeah, and it's not. How are you thinking of it applying here?
The very simple connection is simply that there's a claim on one hand that if a theory makes a prediction before the observation is made, and then the observation is made, that somehow makes it's a better confirmation of the theory than if the theory were constructed, made to measure to fit the data that we already have.
Yeah. Here's what I would highlight that might be interesting relative to your point, is that the Bayesian does not have a problem with HARKing. For the Bayesian, HARKing almost doesn't make sense. Right? That when you formulate the hypothesis, it's neither here nor there to her. Right? He says, okay, you have your data, you have the likelihood of your data. If you have your prior, maybe I have my prior, I don't have, there's nothing more to say than that. And I really don't care when you formulate your hypothesis. Now, if in the kind of modern state of science, we imagine kind of Bayesian meta-analyst looking over the state of the field and asking, do I want a literature composed of studies that are reported in a kind of in the way they are now, like significant, not significant, but without access to the data? Would I care if they're HARKed or not? She would object to HARKing insofar as it decreased the informational content of the signal. She would say, if you're she would just like you to give you her data. She'd say, just give me the data, I'll update. I don't care about this HARKing business. And she's done. But if you're only giving her a signal like significant, not significant, she would modulate her prediction the way we would informally, based on a judgment of your prior. If your prior is good, I should know whether you pre-committed to the hypothesis or it just happened to be significant given your results. She would want to know that if she doesn't have access to your data. But in general, the problem becomes obviated for her. That?
Yeah. Yeah, thank you.
So thank you. That was a lot of fun. It does make me wonder whether or not you've given us a reason why there's so much theory generation in social science that goes nowhere. Like there's been this complaints about social science just sort of generating one small theory after another, and that suggests that perhaps people are doing a lot of HARKing and then telling a story about why that's the right theory after the fact, and then it just doesn't seem to go anywhere. And so I wonder if that's what you think is going on. And then I want you to say more about what you might think would happen if we actually, instead of encouraging p-value and for a standard for publication, went with registered reports, said like, we're gonna do registered reports, we have our minimum standard of power instead of a p-value concern. And would that create potentially pernicious incentives as well? Or do you think that would just be epistemic?
Yeah, great question. So I think what you described is exactly right, that we have good reason, just as you say, to think that is what's happening, right? We find results, and we're exceptionally good at telling stories that make those results seem obvious or compelling. Now, what the contribution of that is in character and magnitude to the lack of progress in the social sciences, the kind of development of theory, I think it's beyond, that sounds like a very complicated question. And I think when I look at the problems of theory in the social sciences, that feels like a very kind of just a deeply tricky problem, which is more than even the problems that are indicated by the replication crisis. They're certainly deeply influenced by it. If we had good theory, we notice, right, then you can even have poor tests and you have more reliable literature, right? So how strong our theory is deeply important. The question of navigation space toward better, or what's contributing to weaker theories in social science, the complexity of social, I don't know. I'd love to hear more from everyone here if you think about those kind of questions. What sounds like a better future state? I think I'm definitely strongly in favor of pre-registration generally. Registered reports is one kind of particularly salutary form of that. And I think in a way that many of the folks at the Open Science Framework and the Metrics Project are sensitive to, we want it to be modulated to the field. Like many of the results that I'm going to show here in another work are deeply about, it really depends on that field. It depends on how strong the theory is, exactly as you said. It depends on the statistical methods there. It depends on the prevalence of questionable research practices. It depends on what matters in terms of what's valuable to pursue and what the character of those questions are. And I think we want to pull those together into more rigorous, reflective, considered frameworks in which you have, say, folks in the field come together and decide together, do we want 3 types of registered reports, right, or pre-registered studies, one for exploratory work and one for confirmatory work, one for moonshots in our field that are sensitive to our particular challenges and purposes. And I think that would be the kind of picture of a better future state, or beginning to sketch it. Will we have incentive problems? I think we're going to keep having them. I think it's valuable to keep thinking about how to mitigate them and to align incentives with kind of behavior that we want. So I'm up for trial and erring in that direction. But I think you're absolutely right that I would be surprised if we could get to the happy state where we don't have social dilemmas in science.
Well, this is fascinating. I wanted to ask, basically, maybe in some ways, this question about the scope of the model, or what happens when we introduce some complication. So I want to distinguish between like scientists' ability to like judge whether a given hypothesis is going to be true, like for example, what those prediction markers I take would be testing, from like the ability to select a hypothesis that's going to be fruitful for them to pursue. And there are all sorts of other incentives involved in that respect, like the most salient one being I want to find something surprising. The scientist is actually choosing what to study. Is not like sitting back and evaluating others' work. They're sort of solving an optimization problem, which is like on the one hand, sort of I gotta have something that's likely to give me a result. On the other hand, it's gotta give me a punchy result when I get it. And I was wondering basically how much when we introduce that incentive that could mess with the dynamic. So like, suppose now our scientists are deciding between like either I just predict, I can only choose one and I'm solving this optimization problem there, versus I test them all and then I predict, I choose something like the most surprising or something like that, significant one that I couldn't, just math problem, like how does that affect the dynamics? But I had the sense that for certain ways of setting up maybe the hypothesis space, for example, suppose like there are a few hypotheses that are quite probable and a ton, which are like really surprising if true.
Yeah.
Like, you could get incentives that would lead like the second strategy to like, I don't know exactly how to basically lead to a lot of results that seem really surprising from the HARKing strategy that you want.
That's right. So that would just as you say, if you open those degrees of freedom and they have the scientist has sufficiently many hypotheses to choose from, and she's following pick the most surprising one that's also significant, definitely lower the reliability, increase the false discovery of hypotheses produced by that method. That's absolutely right. And that would also wouldn't be super surprising if there's at least some element of that in the wild actually going on. Right, we have those kind of suggestive results like highly prestigious journals produce, right, findings that are less likely to be true, right, on average. And we think that because the plausible explanation is it is the fact that the highly surprising result is more noteworthy, more likely to be published in them, and less likely to be true. And so a similar mechanism could be at play. I think your observation's right, and that is one more wrinkle that one would have to consider. And we'd have to think through, how much do we think that's actually going on, and maybe even see if we can get estimates of that under different conditions. And one way that, I think there are a few places where you might get it. There are studies that do kind of multiple testing, and then they also ask for researchers' bets over the multiple tested, and they see what the difference between that kind of background likelihood of a hypothesis being true and the researcher's judgment for those multiple tests is, right? And you could compare those to cases where they hadn't been doing that clear methodology, and the researcher had been just doing her own kind of strategic multiple testing for publication purposes, because these remove that same incentive, right? And see if the daylight between the two of them might give us an estimate of the degree to which the sort of thing you worry about is actually at play. Yeah, that's a lovely suggestion. And that sounds like a plausible dynamic.
Ryan.
Thanks a lot for the talk. So I've got a question that's a little bit more than half baked, but not too much more. So I don't think that there's anything wrong with HARKing, but I think you've explained to me sufficiently what it is, and it's because the researcher, by picking a particular hypothesis, that counts as evidence in favor of that, right? But formally, when you try to justify this, I'm curious how you're doing it, because the space of potential hypotheses is presumably countably infinitely large. And if you're talking about a hypothesis that involves a parameter value, it's uncountably infinitely large if the parameter is continuous. So have you thought about formally how you can justify this claim?
Yes. So the thought here is, and then this particular model is one that's kind of drawn from the literature. The conventional one used by Uniti, early 2003, by Mohseni and Trifolo, and the particular assumption there is, well, not perfect, quite a bit less daunting than that. Even though I think there are measured theoretic ways when one could also make the case that you described, yield at least some kind of mathematically respectable quantity. Here, what you want is that the set of hypotheses is delimited simply by the dependent variables I measure. So if I go into the particular test and I measure things like blood pressure, red blood cell count, and so on, I measured a number of things, height, right? Just their combinations, the sort of ways that those could be associated with the outcome variable of interest produces the hypothesis space. So it's finite.
Okay, good. So this is the lead into my second question. It seems like there are really two selection procedures going on. There's the initial ruling out the nutty hypotheses that no one's considering. And
By
then,
choosing which dependent ones you consider at all, right? I don't measure their zodiac sign, is what you're thinking?
well, in reality, you do more than that, though. I think you sort of intuitively think, well, there are a bunch of hypotheses that, I'm going to assume my blood pressure doesn't cause me to smoke, for instance, something like that. And so then it seems like there are two selection procedures, just initially ruling out the hypothesis we know to make no sense, and then choosing from among those one or two. And
Yes. I think that's exactly right. I think that's a nice observation for like the deep assumptions about this kind of context of inquiry. You're right that when we're even talking about the researcher's judgment, it's relative to pick the set of things that you could think could work in this study on kind of this sort of health outcome.
Right, but then I wonder if that's going to belittle how much weight we should attach to the researcher picking a particular hypothesis, given that she's already operated in a space of hypotheses that she thinks are going to be plausible.
I don't think it should make any pragmatic difference there, because once I've got those hypotheses, I can just ask about the quantity of. I can test them all, or I can have the researcher select one, right? I can pick one at random, or I could have the researcher look at one. What's the difference in the likelihood of them being true, right? So I can get the evidential relationship on that conditional relationship without having to worry about accounting for, well, what is the work that the researcher did or the community of researchers did to delimit the set of even measurements that we took, and thereby the hypotheses we could entertain to, like, blood pressure, red blood cell count. But then you're right that is implicitly going on in that scientific inquiry. In the deep prior of what's at play, we rule out zodiac sign, number of particles in the room, and so on, and get those things. And that's in a sense a part of the community of inquiries prior. So pragmatically, it wouldn't change any of the analysis.
Ready to fight?
Thanks, yeah. So this may just be a less than half big question, but also touches on some of the things that come up. So I just think back to your statement early on that physicists have highly significant results, value, p-values that they get.
The 5 sigma.
That's right. But also it strikes me that what's not going on there is kind of null hypothesis. In the sense that they're often got some highly mathematized terms that then be used to drive the experimental design in a way that makes a severe test between two substantive theories rather than a hypothesis in some. In medicine, it's incredibly different. Right? You just trying to see whether some drug has effect, but you don't have the same kind of theoretical structure. So I'm wondering whether the recommendation at the end is not fiddle around trying to figure out when you should hark or not, but build better theories, which then comes back to some of the other.
Yeah, that's a lovely question. I think I'm definitely always in favor of build better theories. It can be a hard recommendation to make. You're like, just go go forth and make better theories. I think that so. I've not worked through the particle physics literature at all. I've taken kind of just an outsider's view of, hey, notice they have a different conventional threshold. At the level of that level of description, though, that says to me, alpha doesn't make sense unless you have a hypothesis. Right? So it might well be exactly, in fact, I know it is, as you described, that there are deep mathematized theories that are being compared, but I do believe that the hypothesis for them still obtains the level of, did I detect the particle or not? And there it is ultimately at that kind of that level of observation grounded in, I have a significant threshold because I need to get evidence that crosses this, this line in the ground, so I can say I indeed detected the particle, right? And that's the 5 sigma. So they also have, at that level, you're right that there's much more going on more deeply. I believe they do have just straightforward null hypothesis.
Although the theory itself is partly what's driving the.
Yes, that's right.
The predictions themselves are quantitatively much more precise.
That's right. And I think to your point of there's an intuition that the theory matters, and I think that's exactly right. And the way we can think about it in this kind of framework is that it's affecting that prior. Whether it is something very parochial like common sense, like there's some kind of good common sense we have in the domain, or if we have an amazing theory, the ultimate mechanism of proximate action on the reliability of studies is going to be via, before I even did the test. Did my theory tell me that the Higgs boson is there and I should just bet on that even before I detect the particle? Or did my theory tell me that broccoli cures cancer and I should just bet against that even before I, even if I got a very low p-value and so on?
Can I do a quick follow-on on this?
I wanted for okay, that's fine.
I just want to say, like, there's also a wonderful pragmatic freedom that high-energy physicists have, which is that there are very few people who have equipment to compete with them, so they can keep gathering data and not get scooped, right? So they can afford to go for those really low sigma.
And they're being forced to cooperate means that they gather enormous data and that contributes to the same vector. And so they're one of the few places where you won't say, hey, your studies are underpowered. Absolutely.
I think I meant my sharing. But just a quick follow-up. I mean, I think
to Colin's point, I think here's a distinction between the nil hypothesis and the null hypothesis is the relevant one. They don't test nil hypothesis. They don't set the value of the parameter to 0. They set the value of the parameter based on the theory, but it's still null hypothesis in the sense that they measure the division from a point that's going to work as a point of reference. And you see how unlikely the data or more extreme data would be like in the parameter has this value. So it's still in some way, or still totally null hypothesis. It's just not nil hypothesis. The way it's done in psychology, where the null hypothesis happens to set the value of the parameter of 0. In any case, so my question was about. So I really like it, and I'm quite convinced by the negative parts of the. I'm a bit less convinced by the positive proposal. And the reason why I'm not convinced by the positive proposal is because I at least use my experience, you seem to be misdescribing the way HARKing often happens. The way HARKing often happens, as in my experience, is neither what you call HARKing nor selective HARKing. It's not selecting one of the many hypotheses that are compatible with the data at random that will be significant people are compatible with significant there, nor the one with the lowest p-value. It's to take the hypothesis you were testing and look for a moderator. So you're testing, for example, independent variable has an impact on dependent variable in experiment, non-significant result. Bad luck. Well, what you do subgroup analysis. Men, women, over 60, under 60, over 55, over 50, over 55. Right the people who write with the right hand, who write with the left hand, until you get a significant result. And then you say then you formulate your hypothesis as being IV influences DV and the moderator is H. And that's what you say you've always been predicting from the get-go. So it's not chosen at random exactly.
Yeah.
Nor is it the first perspective. Why does it matter? Well, it matters for two reasons. I'm not exactly sure that hypothesis is less probable than the original one you started with. I think they are actually equally, just because in psychology, for example, the domain knowledge is so vague that I wouldn't bet more on IV causes DV or IV causes DV with a moderator gender. I personally don't think any of them is less likely to be true. I'd be very surprised actually if people have, it's just literally, we can set up priors in any different way. Anyway, but also, so that's the first point. But also this when you start looking at the way hacking happens to be done, at least in this part of science, I know well, it does suggest another account from the one you're describing of ones that connect to a traditional issue, the issue of overfitting. So one of the reasons why HARKing is bad is that you're overfitting your data. Now, you're having a hypothesis that's capitalizing on the noise, whatever source measurement variance, something variance. So you're capitalizing on noise. Now, we should know that. So basically, our prior odds should be such that a hypothesis that's p-HARK should have a lower probability, but not because of background knowledge, the way you describe it, but because we know beforehand that it's going to be capitalizing on noise. So I cannot agree with you that the prior odds are just the right way to look at things. And that's what I can, but it's not prior knowledge. It's more like, what is the bad thing? How bad an idea it is to overfit data?
So I'll start with the second observation. On that one, I think it's important to acknowledge that the particular mechanisms of how overfitting, in fact, lowers the probability, the expected performance of a model out of sample is still mysterious. There's not the account where I'm like, that's definitely what's going on. And it's still very open.
But we know it's true.
Huh?
We know it's true.
We know that it is often true. That's right. And for my money, I would bet that the right account is all again going to be Bayesian. And I would say that it's going, in what kind of Bayesian one, it's going to be something, again, indicating the structure of the background beliefs of, in some cases, the world is simpler. In some cases, it is more complicated. It doesn't seem to me, right, just as kind of so others have worked through it, there's not a reason to expect that, in fact, the world is always simpler. And so when we look at that, you're like, okay, it's got to be something about these characteristic situations that we run into have some property that often, if you penalize a more complicated model, it will be better for different than those pragmatic reasons of, keep it simple, stupid, to build the better thing. and then maybe I don't pretend to have an account there. There might be some formal interesting features for certain classes of models, like if you think of polynomials, right? That does that. Yeah, so there I'm going to suggest, or what I think about loud with you is, we don't know what that is. I would still bet that I would put my money on it being well described by something coming in through the prior knowledge of the given situation that makes overfitting bad. And when I've thought about p-hacking in the past, it's not obvious that it's the same precise flavor of overfitting that I get when I go up in degrees in a polynomial. And the way I think one very plausible way of thinking of it is any of those things that we were likely to say, like the precise hypothesis with this method of measurement, right? And these background assumptions and this way of measuring data and this way of including and excluding outliers, right? Was that one likely to be true, right? The answer is not on its own. For any given, if I make the kind of band of conditions, very much in the sampling style account that I think you've nicely articulated in the past, when you think through that sampling account, expecting to be exactly right in any given world is not quite right. And then when I pick a methodology that by construction picks one of them out and gives one of these unlikely worlds to me, I should almost think that there's very little evidential weight, because I knew you were going to give me one. I knew none of them were particularly likely. And it was also why, if you show me that almost any of these assumptions, right, you sample from a broader set of them, show kind of robustness of your results, now I'm starting to update more reasonably on your findings. So for that one, I would say that my sense is ultimately, if we think carefully about it, it will be something, a mechanism acting through ultimately the priors about the context of inquiry and the situation we're learning about. I think that'd be worth thinking through, and even maybe we can sit down and work out together how that might be so. For specific things like p-hacking versus multiple testing versus and for the first one, I really appreciate that observation of thinking carefully through, okay, there's a style of HARKing, which is my hypothesis didn't work. And I go to a pretty logically independent hypothesis, meaning that I thought it was broccoli, but I also tested celery and celery works. So they're like, no, I thought it was broccoli generally, but now I found that it's broccoli for Latino grandmothers. And that was the subset of the data that came up significant. And there the suggestion is, look, before the test, I shouldn't have been more or less confident in Latino grandmothers versus just broccoli as a good effect for the outcome variable in Latino grandmothers that I should have had for broccoli having it in general.
Without enough relations.
Yeah.
So it's not quite, it can't be quite right, but close enough. Close enough in a way that's not going to matter. So I mean, they can't really be equal, obviously. But
that's right. And I'm thinking that might be actually where the effect is taking place, is when we do kind of subgroup analysis and we pull out a piece, what we're missing there often is the following, is that the actual hypothesis that was vindicated, the evidence that we got was for all these other ones. Imagine the general hypothesis that we're interested in is something like, does broccoli have an effect on this thing? And if broccoli had an effect on the grandmother, a deeper model would say, well, why shouldn't it also have an effect on people who are less than 65, right? So it is in every other group, in every other subgroup in which it's failing to produce that data, that should be something we're updating on. But then at the end of the day, we just report that one, and then we tell the story without kind of weighing the evidential character of all the other subgroups. And so that again might be, that would be the issue there rather than, that seems to me at least plausibly what's going on with the particular challenge of subgroup analysis, is the failure to articulate the evidential weight of all the results for all the subgroups and kind of telling a story post one portion of it. And the question is that the same sort of HARKing as here?
well, it's not the same. The question is whether
Well, yeah.
the broader story you're giving can be applied to.
Just so. Yeah. No. So that because we're saying that I would have to think about it more. I would say that it certainly, this sort of HARKing applies to some, the class of, I thought broccoli, I found celery. It wouldn't apply to, I thought broccoli, but I found broccoli for some subgroup of broccoli. Yeah, so it applies to the former. And I'll think more with you about the latter. That's a great question. I appreciate it.
Merci. Before we stop, let's thank you again for coming. Remember, on Friday it's online at noon. Register if you want to attend. And please, if you haven't done it, write your name on the sign-in sheet at the entrance. So we can do some tracking in case you go.
So the 6 of June.